Welcome to our channel, Square Ekpatshala, your home for physics mastery. Light is the exact form of energy that triggers the sensation of sight in our eyes. But depending on the surface it hits, light can play tricks on us. This split-screen diagram illustrates two very different real-world reflections. On the left, a flat mirror perfectly reverses the word ambulance from left to right. On the right, a curved rear-view mirror compresses a massive wide-angle traffic scene into a tiny piece of glass to keep us safe. To understand exactly how to control and manipulate these optical illusions, we have to master the physical rules dictating how light bounces. We need to look closely at the laws of reflection. We start with the simplest baseline, the plane mirror. This diagram shows a flat mirror's cross-section. When an incoming or incident ray strikes the surface, we draw an imaginary vertical line at that exact point, called the normal. The core rule here is absolute. The angle of incidence coming in perfectly matches the angle of reflection going out. Because of those matching angles, the image you see forms directly behind the glass, where light rays only appear to meet. That creates a virtual, erect image. And importantly, the distance from the object to the mirror in front is mathematically identical to the distance of the image behind it. We can apply that equal distance logic to real-world calculations. If you sprint toward a mirror at a velocity of v, your reflection closes the gap from the other side at the exact same speed, meaning the image appears to approach you at twice your velocity. And if you want to see your entire body from head to toe, you only need a mirror that is exactly half your total height. Plane mirrors give us a perfectly predictable one-to-one reflection. They are our control group. Now we introduce curved geometry to see how those exact same rules stretch and shrink reality. Here we see a hollow glass sphere being sliced down the middle to create spherical mirrors. If we take one of these slices and coat the outside surface with silver, we get a concave mirror. If we coat the inside, leaving the bulging outer surface to reflect the light, we create a convex mirror. To map the light on these curves, we use three anatomical landmarks. The exact center of the reflecting surface is the pole. The center of the original hollow glass sphere becomes our center of curvature, and halfway between them sits the focus. That simple difference in curvature dictates their physical function. Concave mirrors capture light to magnify objects, like a dentist inspecting a single tooth. Convex mirrors diverge light to shrink objects, which provides the wide field of view needed for parking garage safety mirrors. To predict exactly what those mirrors will show, this diagram tracks three standard paths. Rule 1. Any ray traveling parallel to the principal axis reflects directly through the focus. Rule 2 is the exact reverse. A ray passing through the focus reflects parallel to the axis. And Rule 3, any ray coming from the center of curvature strikes the mirror at 90 degrees and bounces straight back along its own path. An object emits an infinite number of light rays, but you don't need to track them all. By tracing just two of these standardized paths until they intersect, you can mathematically locate any image in space. We can prove the precise geometry of that focus point. Look at this diagram isolating the incoming ray. Because the incident ray is parallel to the principal axis, the alternate interior angles, angle AIC and angle FCA, are equal. According to the laws of reflection, the incident and reflected angles also match. This gives us an isosceles triangle right here at CAF. Because the two angles match, the two sides match, proving mathematically that the focal length is exactly half the total radius of curvature. Now we build the primary mirror formula. This diagram tracks an object labeled AB, sitting far out past the center of curvature. Following our standard ray paths, the light bounces and intersects to form a real inverted image, labeled A'B', between the center and the focus. By drawing lines from the object and the image directly to the central pole, we lock in two pairs of similar right triangles. Because the angles of reflection at the pole are identical, and the vertically opposite angles at the center of curvature match, we can establish direct algebraic ratios, matching the height of the object to the height of the image. Setting those side length ratios equal to each other gives us an equation charting the exact distances of the object, the image, and the focal length. By dividing both sides of that raw equation, by the common denominator UVF, the math distills down to the universal mirror formula, 1 over F equals 1 over V plus 1 over U. These steps prove that a distorted reflection in a curved mirror is highly structured. The resulting image is strictly bound by the geometric rules of similar triangles. 99% of errors in optics calculations happen because of a failure to apply a basic XY graph. This diagram fixes that by placing a standard Cartesian coordinate grid perfectly over the mirror's pole. Once the grid is set, the rules are rigid. Because light travels from left to right, we measure against the flow. Therefore, the object distance, or U, is always a negative number. Since a concave mirror focuses light in front of itself on the left, its focal length is negative. A convex mirror focuses light behind itself on the right, making its focal length positive. Let's test that logic. A dentist holds a concave mirror 2 centimeters away from a tooth. The mirror has a 5 centimeter focal length. Based on the XY grid we just built, what are the exact positive or negative signs for those two variables? The object distance, U, is always negative, so it's -2. The mirror is concave, so F is -5. Plugging those strict negative values into the mirror formula guarantees you find the correct image location. Once you have that, you can define the image's size using linear magnification. This visual breakdown charts the magnification formula, denoted as M. If your final calculation for M drops below 0 into the negative, your image is hanging below the x-axis, meaning it is real and upside down. If M is positive, the image sits above the axis, making it virtual and standing straight up. Combining the mirror formula with a strict adherence to that Cartesian grid eliminates the guesswork. It guarantees you can mathematically predict the behavior of light hitting any spherical surface. Before we finish, let's look at one final visual trick. When you angle two plane mirrors toward each other, the light bounces back and forth between them. The exact number of duplicated images is dictated by the angle. You take 360 degrees and divide it by the angle between the mirrors. As the mirrors close in, the reflections multiply. If you push the mirrors until they are perfectly parallel, the angle hits 0. Dividing by 0 pushes the math to infinity, creating an endless tunnel of reflections, like sitting between two parallel mirrors at a barbershop. This master cheat sheet pulls together the 4 physical rules of reflection we've mapped today. You have the UVF mirror formula, the magnification ratio, the absolute Cartesian sign limits, and the geometric proof that the focus is always half the radius. You have successfully locked down the fundamentals of ray optics, Part 1. Make sure to subscribe to Square Ek Patshala, because next time we break through the glass to derive the laws of refraction and build the lens maker's formula.